All right, so what we have is we have an atom where you have protons and electrons, uh, and the electrons are outside the atom. And right now they don't seem to have any position. They're just flying around randomly, for all we know. And but there's difference between protons and electrons, and and electrons aren't collapsing, and that's a mystery. Uh, and the other thing we talked about was light, and we're going to apply that to this next section, right? And now about 1900, it was pretty much thought that era all of physics was all they just had a few things to figure out, and it all was taken care of. Um, there was Newton's equations explained everything. Maxwell's equation explained everything. Um, and there were just a few questions, and they just thought they could check them off, do a few experiments, check them off. And one of the experiments that one of the things that was kind of a mystery was something called the black body radiation. But before we talk about it, I want to talk about distribution or graphs, uh, because it really is an important concept here. So okay, distribution graphs are essentially histograms, bar graphs. Okay, so you have here that this must have been a population of people, and we measured their ages. You have between 20 and 30, 40, and so forth. Now you can consider each one of these boxes as bins, okay? And the height of the bin is how many uh, people there are or parts, ages are inside that bin, okay? So, so this right here between 20 and 30 is a bin that holds two people, let's say, right? Between 30 and 40, it looks like there's four people, and so forth. So, uh, so distribution graph, a bar graph, is essentially just a grouping. All right. So you have bin, 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 and bin. Okay, and you look at each bin has a very okay. There's something called a normal population, normal distribution of whatever, and the bins follow this shape. You've seen this, okay? It's called the bell curve, and it's very regular, and it's found in nature all over time. It just says is that you have very low at one end of bin. This bin is very small, and the average is the most, it's the biggest bin, and so forth. Now, we see about 15. Now, the curve, you see that you have a curve that's continuous that fits this, okay? Now, this curve has a calculus formula that comes up with it. And it's a continuous curve. And what it says is that all the bins are infinitesimally small, but they still have, they're not infinitely small, okay? They're small, but they all still have a width, okay? But that width is that we just can't measure it. And then when you add all up their widths, they give this shape, okay? But and that's why you have the small curve. But what you can do is you can break this up into really, really tiny bins like this. Okay, now if you've had so it's really not continuous, but in calculus we do call it continuous because of our infinitesimal properties here. Okay, uh, and uh, and if you've had calculus, you've you've learned about this. Okay, so if I were to write the actual equation for this, you would see that it'd be a derivative and so forth. Okay, uh, but that doesn't matter. What matters is this: is that there's distinct boxes, okay? But the boxes are are infinitely small in their width. Okay. Now, fella named Wolfgang Boltzmann, and we talked about him, and when we talk about gases, came up with the Boltzmann distribution. And Boltzmann distribution uh, tells us how particles are distributed inside a system uh, according to their energy. So, and they will have this kind of, it's not a normal distribution. So you'll have, there will be a, like an average, but kind of a different average, or it's just because it's not in between everything. But there's, I guess, most probable, okay? But it has this quality where it has a short tail and then it has a long tail, all right? Now, okay, now, technically, well, this is that, again, this is a, if when you did the calculus, each one of this thing is broken up into tiny bins as well. All right, but it's not a normal distribution. Okay, so how does that relate to the black body um, mystery? Okay, so the black body mystery goes like this. So if you have a steel box, it can be made of, not just steel, but metal box, and it can be made out of any metal, which is kind of an interesting thing. And then what you do is you have a little peek hole that you can look inside it and see what's going on, right? And then maybe you have a device that can measure what light, like a prism or something that can measure the light that's taking place. And then what you do is you heat it up. You maybe have heat it over a fire or something. And what happens is inside the box the color starts to change. It starts to turn red, and then with more heat, temperature turns orange, and then yellow, and then blue, and so forth. Okay, and then finally violet. And so the question is, why did it do that? Okay, what caused that change? Okay, so and with so they came up with so this is the graph that they came up with. Okay, so this empirical data of a black box is that. So let's take a look at this guy down here. And so what they did was they looked at the wavelength of the light. We talked about wavelength, and they used the angstroms, okay, instead of nanometers, but doesn't matter. But and this is low temperature, lowest temperature, 3000 K, and it had this shape here. And the thing to notice about it is the shape. Okay, it has a short tail and a long tail, and it has a sort of high point. Right, now when you raise the temperature, it keeps that same shape, but it gets more distinct. It still has a high point, and it moves over, so the wavelength decreases, which means the frequency increases, and you still get the tail going down. All right, and then what you get is if you increase the temperature again, you get this shape here, okay, and then it comes back down. Same properties. So it seems like the short tail is getting shorter and shorter, and the long tail is getting longer and longer, but it's getting higher. Okay. Okay, it seems to be this is that the intensity of the wave is related to how much the wavelength. Okay, all right. So what what scientists and mathematicians try to do is they try to come up with a mathematical formula that would fit, that would work to fit this curve, and then that mathematics should be able to describe its physics, just like F equals ma is a mathematical formula, but it says as you increase the mass, you have to increase the force. If you increase the acceleration, you increase the force as well. So the math has to equal, has whatever math you come up with has to be, has to mean something. And so enter the most famous theoretical physicists at the time. And this is like 1900 when this is really coming to the forefront. Okay, so these two guys here, Raleigh Jeans and Wine, were two of the most prominent theoretical physicists that applied math to physics. And what they did is both of them took a look at it. And what Raleigh Jean came up with is that he came up with an equation that fit this side of the curve. And Raleigh Jean, got these backwards. Wine's law came up with the other way, all right, like this. But neither one of them fit the proper curve. Now, Wine's actually said as you keep on heating the box up, it will keep on heating itself up until it gets so hot that it becomes indistinguishably hot. All right, so it just overruns, and so it's a catastrophe. So it says that if you heat anything, everything will just gets overblown hot. That didn't make any sense at all. So both these guys' equations didn't work. And then there's a guy named Max Planck, all right, and you don't have to worry about the equation here. The Max said, "Hey, I can figure this out. Just give me a day." It's kind of a curious thing, is that when he saw this curve, he goes, "Oh, I can figure that equation out," and somebody showed it to him at a party, and he goes, "Oh, I can do that," and he went and he figured out the formula to fit this curve. Okay, and it was perfect. Okay, his equation found by fitting formula to a curve. So what he did was he found an equation that fit the curve. It worked, but the problem is this: it didn't describe the physics. Okay, just like F equals ma, you just can't say F equals ma. Okay, you have to tell that what F and ma mean and how they relate to F. Okay, when he came up with his equation to fit this curve, he just said, "I have an equation to fit this curve." And he didn't like that, and he knew that he could never present this unless he could do that. So he had to try to explain it. So he knew that he used Boltzmann's distribution to figure this out. And so what he said, and he didn't like doing this, is he said there were bins of frequencies. Okay. And they had actual sizes. So this wavelength has a size, and it can hold a certain amount of intensity. And then the next bin has a different size. And so you don't continuously, you just don't flow from one bin to another bin. You have to jump from one bin to another bin. Okay, now, and what, from his work, he found out that the sizes of the bins, okay, this length here, okay, the width of the bins had a very distinct number. Okay, 6.63 times 10 to the minus 34th. That should be joules times seconds, and it's called Planck's constant. So it's so small, but it's not infinitesimal. Okay, so if this was continuous like a normal distribution, all these would be jammed together. But actually, these guys actually have a width about them, and that was weird because going from one frequency to another frequency wasn't just continuous. You had to go plop and then jump. Okay, you physically had to go from one to another. It wasn't just a flow. So this is not continuous. Okay, this is not continuous like Maxwell's, or it's just not continuous like normal distribution. So Planck was able to simplify his equation to the energy of a wavelength is equal to his constant. So basically the size of the bin times the frequency is equal to its energy. All right. And 6.63 times 10 to the 31st. And this is just another unit. All right. So E is the energy of the black box. Nu is the frequency of light emitted by the black box. And H is what's called Planck's constant. Okay, now what we're going to do is kind of start putting things together here. All right, now let's talk about light and the photoelectric effect in Einstein again. So I talked about his annus mirabilis papers. There was the Brownian motion, there's theory of relativity, and there's the other one, the photoelectric effect. The photoelectric effect said this. Okay, so what Einstein tried to do is there were some experiments that said is that if you took a metal and you radiate it with electromagnetic radiation, there's only certain electromagnetic waves that will cause electrons to be emitted. Very specific wavelengths. Okay. So Einstein just sat around, thought about that, and he knew about Planck's constant and idea. So 1905, Planck came up with this idea in like 1900. And he said the reason that this happens is that light changes from a wave to a particle, okay? And when it does that at the right wavelength, so this electron right here, okay, to get it out of this metal needs a wavelength, a very specific wavelength, okay? Well, when that wavelength comes in, it kind of, we can say, change into a particle. And when it does that, it's like a billiard ball, pool ball, smacking another pool ball, the electron, and knocking it out. All right. Okay, the electron needed an exact amount of energy that was related to a wavelength or frequency, because if you know a wavelength, you know a frequency. And so Einstein said, well, how does energy and frequency relate? Well, it relates through Planck's formula. And so what Einstein said is that the amount of energy needed to, he could predict the wavelength and energy amounted to knock the electron out using Planck's constant. All right. So we knew that electrons could be knocked out so electrons could be moved by light, by photons, okay? So if you have an electron, the thing that can knock an electron out will be a particle of light, Okay, and that's what Einstein came up with here. Okay, so what this basically says is we have this equation here is that the energy is equal to Planck's constant times the frequency. So if you increase frequency of electromagnetic waves, you increase its energy. And so here's a graph. So here you have wavelength up here, frequency up here. We'll look at the frequency. And these are types of waves that were common in our world. Okay, so our visible is right here, and there's frequency or wavelength here. But the energy, if you plug this in, will be this number down here. All right. Now, if you increase the frequency, okay, like the ultraviolet light, which has a higher frequency, what you do is increase the energy. So ultraviolet light has a higher frequency. X-rays have a lot of energy because they have high energy. High frequency. Gamma rays have even higher frequency. Now, this is important because if you get an X-ray, go to a hospital and get an X-ray, they will make sure that they'll protect you from those X-rays by putting lead on you, lead apron on you, or whatever. And I don't know if they do that more, but they used to. And that's because if the X-rays come in, because they're so high energy, they'll actually damage your DNA. And that's also what the ultraviolet waves do, wavelengths do, and that's one reason why they cause cancer. And sun gives off ultraviolet, and that ultraviolet rays can cause skin cancer by the energy can mess up your DNA. Now look at here where here's our visible. Infrared has lower energy than visible. Microwaves even less, and radio waves even less. Okay, so your microwave that you cook food in actually has less light, has less energy than what's coming out of your light bulb. And radio waves like your cell phone and so forth, they even have less energy than that. Okay, so when they used to say that having cell phones they could cause cancer because it's giving off electromagnetic waves. Those electromagnetic waves have really low energy, so the possibility that happen is probably very, very, very small. Okay. All right, so that sort of gives you an idea about the electromagnetic spectrum. So let's look at waves a little bit more and particles. So there's a difference between waves and particles, obviously. Okay. Well, one of the big differences is their energies. A wave energy, and we talked about this before, is dependent on how big the wave is. All right, that right there. A particle's wave is how fast it goes. So it's different. It's important to know the difference between these two. Is that waves have two different kinds of energy transfer, and it turns out that light behaves both like a particle and wave, so it seems to have both of these qualities, and we call it duality, right? So light can behave like a wave or particle depending how we want to look at it. When it knocks electrons out of metals and others that we're going to talk about in the future, it acts like a particle. But when we measure like the reflection and diffraction and things like that. All right. Now, J.J. Thomson's experiment can be done with any gas. So when he took his tube and put a gas into it, it gave off light. And so if the original idea of electrons are just flying around. Say if you have your protons here, you have electrons flying around. Okay, those electrons could be in any energy, right? And so sometimes they could let off a little bit of energy, so that'd be like red. Sometimes they could give off high energy and be like violet. And so you would expect to see the white white light like you do, like the sun, and with a prism you would see the rainbow spectrum, and it'll all be continuous. Like the blue turns into lighter blue, and so forth, and turns. So it's all continuous. So that's the kind of thing we kind of expected, is that when you put a gas inside a container, turn it on, you expect it just to be white because some of the particles are low energy and some are high energy. And we do see this, okay? We see it with visible light, like the sun, okay? If you were to look at a light bulb, and if you look at anything that's really hot, okay? So that's indeed what you do see. However, if you take a pure elemental gas like hydrogen gas, we get only one color being emitted, or any other element. So here there's helium, neon, argon, krypton, xenon, hydrogen gas, deuterium, which is a hydrogen with a neutron, nitrogen gas, oxygen gas, and mercury gas. And if you look at all of these guys, they're not white light. Okay, they all have their very specific colors. Okay, so every element has its own specific color of light, and actually we use this. So when people, astronomers look up in the sky and they tell you what certain stars are made of or whatever, it's because they look at the color that's being emitted. If it's giving off this color and this color here, they know it's mostly made of oxygen and mercury. Okay, so okay, so that's cool. But now let's take a little bit closer look. So it's not white. So they're very specific colors. But let's look even closer. Okay, so just like if you took a white light, okay, and I don't know. Hopefully, you guys have seen prisms before, but if you have a prism and you look it up in the sky at the sun, you'll see the rainbow. So you can do the same thing with these. So here's your gas. It might be hydrogen gas. It might be this pink color here. Okay, that happens when you light up, when you give energy to hydrogen. And then what you do is you have it look through it at a prism. And what happens is that you get this, you don't get a complete spectrum. You don't get from red to purple or violet all in one. You get very distinct bands of colors. Okay, so it goes from red, and this is the orange, and then there's the yellow, and so forth. Okay, and it turns out that every element will have different bands. Okay, so by looking at these bands, so this is hydrogen. So this is looking at spectrum of hydrogen, and what was wondering is that can we predict where these lines are? And so one of the mathematicians at the time, so this, by the way, you could do different spectrums, and this was done by a guy named Balmer, came up with this spectrum right here. There's other spectrums as well, but that's not important to us right now, but it's important to Balmer. is that what was found out is that you could actually you could actually predict where these bands were. Okay, if you knew where one of the bands were, okay, maybe like this guy right here, and we'll call that guy 2. We could figure out the other bands. So let's say this band 2, this one's 3. Then we could figure out the wavelength for each band. So this is band number 3. I could figure out its wavelength using this formula. Okay, and the key thing here is this constant here called Rydberg's constant. So you can figure out the wavelength by just looking at the bands. So if you know this band here and this band here, you can figure out this wavelength. All right, so say this is band number 2, and this band number 3, you can figure out the wavelength of band number 3 by plugging it in this formula. Okay, the atomic spectrum, for most elements is very complicated. So what most scientists did at times, they just focused on hydrogen because it seemed to be the simplest. Balmer, Balmer is actually not the guy that came up with the spectrum, but he actually came up with that equation. And Rydberg's was the constant that we used. Okay, so we have Rydberg's equation. We have Rydberg's constant. Okay, so these are the things we can be used to calculate the spectral lines of hydrogen and so forth. And we're going to do a couple problems. So there's the equation. So if you know N and N2, you can figure out the wavelength of N1 or N2 based on that. If you know N1, you can figure out an N2, you can figure out the wavelength of N1 or N2. So let's see how you do that. So we have Balmer series, N1 is equal to 2. And we want to calculate the wavelength for that's given off from going from one line to line 6. Okay. Right, and then you plug everything in, and then you get, in line 6 is going to be the 6th line is going to be 410 nanometers, which is violet in the spectrum. All right, and you go the other way. So let's say I'm giving you the wavelength, rearrange equations, so forth. And then, so if you give it the wavelength to 650 nanometers, you can figure out what band that is on the spectrum. Okay, from one here, we're going to continue. If we're getting there, so we have an atom. We have the electrons. We still have protons and electrons surrounding. But one thing we do have that's new from what this previous thing is that electrons can be knocked out of an atom by adding light. And that amount of light has to be quantized. It has to be a very specific amount of light that we call a proton. All right. So quantized, and quantized means quantity. So a very specific quantity of energy has to promote an electron out of an atom. Okay, it just can't be some random amount, and that's so we're getting there with what we're gonna do next. Okay, move on.